Swayam Prabha. Digital India. Educated India.
Okay. So, let S be a random subset of the indices. Okay, so let S be this, and I want to show the following, that if I, okay, so let me define the function fs. So, define f of s to be equal to basically the square of the sum. So, sigma I belonging to s x I whole square. And now I will want to ask the question that what is the probability that for a randomly chosen S, okay. So, before showing this, so let us just look at this function. So, what does this function mean? So, suppose if I have the OR, okay. So, if OR of my xi is equal to 0, then it immediately implies that basically for all s, no matter what s you choose, fs of x1 to xn is equal to 0. If the OR is 0, all these xi's are 0, therefore, by definition this is 0. Now, if the OR of xi's is equal to 1, okay, then what we will prove is that for a random s, for a randomly chosen s, the probability that f of s is equal to 1 is at least half, okay. And this is actually quite simple to see. So, how can we see? So, suppose if the OR is equal to 1, then it implies, so if let us say OR of xi is equal to 1, then what do we know? That there exists some k, okay, such that xk is 1, there exists at least one index. Now, I will basically break down this probability into two parts. So, I can write probability of f of s equal to 1 as, okay, I need one more notation. Yeah, I will just, okay, I can just write it over here. So, let me just define S prime to be S minus the index k, okay. So, probability that f of s equal to 1 given sigma j belonging to s prime xj equal to 0 times the probability of this event sigma s prime xj equal to 0 plus probability f of s equal to 1 given sigma xj is non-zero j in s prime times the probability of this. So, this is just by simple conditional probability. Now, I will estimate these two terms. Okay. So, I will basically estimate, so let us say that this term over here, let me call this as 1, and this term over here, let me call this as 2. I will just estimate the probability of 1 and 2. Okay. So, how much is the value of 1? So, 1, note that if this sum is equal to 0, what does this mean? That all these xj's are equal to 0, right, if this sum is equal to 0, which means, and now how do I pick my set S? This S is picked randomly. Okay. So, by randomly it means that each an element is picked with probability half. So, whether to include it in S or not. Now, xk is also in particular, xk is also chosen with probability half, whether it will be included in S or not. Okay. So, therefore, this is equal to half. Okay. Since we include k in S with probability half, right, and a symmetric argument follows for 2 as well. In fact, here the probability is even better slightly. So, here 2 is actually greater than or equal to half, because again, since we are with probability equal to half, k does not belong in S, right, because now note that if sigma xj is non-zero, okay, and if k does not belong to S, then this will remain 1 as well, okay, and that happens with probability half. So, therefore, this is at least half. And now, if I just combine both these two, what I get is that probability f of S equal to 1 is at least half. Okay. So, for S1 up to SL chosen independently, what we have now is that let me just do this like it. Choose these subsets S1 to SL independently and define P of x as in the same manner, but with respect to these subsets. So, 1 minus so I want this 1 minus f of Si. So, basically choose these subsets and for the corresponding and take the corresponding f's for all these subsets and then define this polynomial in this manner. Now, let us look at this polynomial. What is, first of all, what is the degree of p? So, degree of each of these f's is how much? How much is the degree of f of s? 2, right. So, degree of f of s is 2 because it is a square of a linear function, and I have a product of L of them. So, therefore, this degree, I mean there can be some cancellations. So, there, let me just write it as is at most 2L. Right. Moreover, if OR of xi is equal to 0, then P of this is 0 as well by the same argument, and if OR of xi is equal to 1, then what do we have over here? We have that each of these sets is I mean for each of these sets the function f of s is 1 with probability at least half. So, therefore, this product will evaluate to 1, or this polynomial p, the probability that p of x1 to xn is equal to 1 with probability 1 minus 1 over 2 to the power L, right. So, now where are we? So, now we just want to show that, well, if the degree is this, then the error is at most epsilon, which kind of follows quite trivially. So, choose L equal to log of 1 over epsilon. This implies that probability OR of xi is not equal to P of x1 to xn is at most epsilon. Okay. So, in this case there is no error. In this case the probability of an error is 1 over 2 to the power L, and for L equal to log of 1 to the power epsilon, 1 over 2 to the power L is nothing but epsilon. Okay. So, now this is what? So, this is basically over, this probability is over my choice of S1 up to SL, okay, for each and every x. So, for each and every x this is true on my choice of S1 up to SL. Now, what we can do is we can give an averaging argument. So, we give an averaging argument and we can conclude that there exist sets S1 to SL such that the probability that for a random x OR of xi is not equal to P of this is the epsilon once again, okay, and this proves lemma 3 for us. Okay. So, now what do we have to do? Now we have to show how we can use this lemma in order to approximate a ACC 03 circuit. So, now let us get back to proof of lemma 1. So, as I said, our proof will be basically for each gate. So, what we do is we inductively assign a polynomial to each gate in the circuit. And then what we argue is that if for a gate G having input polynomials, let us say P1 up to some Pk of degree at most 2 log S by epsilon whole to the power. So, if for a gate G in level I, okay. So, the inputs are coming from level I minus 1 having degree at most 2 log S by epsilon to the power I minus 1, then the output polynomial of gate G, okay, let us call it as say P of G, has degree at most 2 log S by epsilon to the power I. Okay. So, let me just quickly say what we will be doing here. So, we will be inductively assigning polynomials to each gate. Okay. So, basically we will start at the lowest level, that is with the inputs, and then we will keep on going up. For each gate we will show, and what we will show in addition to this is that, so of course there will be some errors. I haven't talked about the errors over here right now, but what we will show is that the degree increases by a multiplicative factor of 2 log S by epsilon in each level. So, as I go from I minus 1 to I, it gets multiplied with 2 log S by epsilon. Okay. So, finally, if the depth is D, the total degree will be 2 log S by epsilon whole to the power D. Okay. So, for an input variable, let us say xi, you just assign the polynomial xi. So, clearly the degree is 1, so it satisfies our criteria. So, at I equal to 1, the degree has to be if I is equal to 1, then the degree has to be at most 1, which is the case over here. So, this is the base case. Now, let us look at the different types of gates that can occur. So, first let us look at NOT gate. So, NOT is the simplest case. So, what should the polynomial be corresponding to a NOT gate? So, first of all, note that for a NOT gate there is only one input, right. So, what should the polynomial be for the output of a NOT gate? 1 minus that, right. So, it just negates the input. So, if G is a NOT gate, then P of G will be 1 minus P1. So, there is only one input and it is this. So, now of course, here the degree does not increase at all. So, this condition is satisfied and there is no error is introduced. No error introduced. Now, if G is a mod 3 gate, Okay. Then what we will do is that we will define P to be equal to sigma, actually I do not need x1 up to xn over here, but anyway does not matter. So, Pi I going from 1 to k whole square. Okay. Now, first of all, how much is the degree? So, these polynomials had degree 2 log s by epsilon to the power I minus 1. So, therefore, the sum is also the same and the square will be twice of that. Okay. So, degree of Pg is at most 2 times 2 log s by epsilon to the power I minus 1, which is 2 log s by epsilon to the power I. Okay. So, degree condition is satisfied. What about error? So, now note that if all the xi's are 0, okay, sorry, if all these polynomials are 0, okay, then this sum is 0 and the square is 0. Okay. So, therefore, Pg is equal to 0. So, if sigma, now if all Pi's are equal to 0, then Pg is equal to 0. On the other hand, if there exists some Pi, if this, well, I shouldn't say, yeah, so exactly, so I shouldn't, I'm just thinking of the best way to write this. So, yeah, I shouldn't say all. So, let me just put it this way. So, if the sum of Pi's is equal to 0 mod 3, okay, then Pg is equal to 0, and if this sum is non-zero mod 3, then it can be what? It can be either 1 or 2, so that is basically 1 or minus 1, in which case, because I am squaring it, P of g will also be non-zero, right. So, this is a if and only if condition, right. So, even in this case, no error is introduced. So, this takes care of the mod 3 gate as well. Now, we come to the most interesting case, which is OR gate. So, if G is unbounded OR, and we do not need to consider AND gate, because it can be shown in two ways. One is we can remove all AND gates using De Morgan's law, that is one way, and the second way is even if we have AND gate, the proof for AND and OR is very similar actually. So, one can imitate it. So, if G is AND gate, then we define Pg. So, now you can guess what it will be. So, it will be 1 minus product of so how do I write this notation? So, what I want to show here is that if I have an OR gate, then I will take L subsets of 1 to k, and for each of those L subsets I will compute the function f of s, and I will just write one product of 1 minus f of s. Okay. So, it is 1 minus of f of s I going from 1 up to L, where f s I is basically sigma p, let me use I haven't used J here, let me use J, Pj, where J is chosen from S. I. Okay. Si is a subset of 1 to k here. Okay. So what I will do is I will choose Si randomly from 1 to k, and then I will construct I will define f of Si in this manner, and I will define Pg in this manner. So this is exactly what we did in the, or what we did for lemma 3 over here. Okay. So we will just use the result directly by lemma 3. There exists choice of S1 up to SL such that probability that OR of my PIs is not equal to Pg is at most so this actually depends on my choice of L over here. So here I will choose L a little differently. So I will choose L. So what was my L earlier? Earlier L was log of 1 over epsilon. So here I will choose L to be log of S by epsilon. So since L is equal to log of S by epsilon, this will be epsilon by S over here. Okay. Now why am I choosing L to be log of S by epsilon? So that will be clear once we compute the degree of this polynomial, because I have to bound the degree. Okay, so let's just analyze this quickly. How much is the degree of Pg? Okay. So how here basically each, okay, so by induction what we have is that each of these Pj's have degree 2 log S by epsilon to the power I minus 1, right. So therefore this square of the sum will be twice of 2 log S by epsilon to the power I minus 1, and this product will be L times that, right. So this degree is at most, so first I have 2 log S by epsilon to the power I minus 1. Now I take a square over there, therefore this gets multiplied with 2. I take a product L times, therefore this gets multiplied with L over here. And here I am choosing my L to be log of S by epsilon. Now you can see why I chose L to be log of S by epsilon, because I want it to basically match my induction hypothesis. I want it to match this S by epsilon term over here. So for my choice of L given over there, this is equal to 2 log S by epsilon whole to the power I. Okay. Yeah, and so my degree condition is satisfied. Now how much is the error that I have introduced at this gate? So the probability of an error is epsilon by S for one gate. The total size of the circuit is S over here. Okay. So therefore let P tilde be the output of the circuit by induction, we have that degree of P tilde is at most 2 log S by epsilon whole to the power d as we wanted, and the probability that P tilde differs with my function f. Okay. So, basically there can be an error potentially at each and every gate. Probability of an error at one gate is as epsilon by s. So, by a union bound we have that this is at most epsilon by s times s, which is epsilon as we wanted. Okay. So, this was the statement of lemma 1. So, this shows us the existence of a polynomial of degree at most this, which agrees on epsilon fraction. Okay. So, now basically this probability is at most epsilon, which means that for epsilon into 2 to the, for at most epsilon into 2 to the power n many inputs, it might differ. Okay. Okay. So, I will stop here now. Yeah, so the remaining part, that is the proof of lemma 2, I will do it next time. Okay. So, thank you.